for those who are trying to figure out if I have to take the final or not. So I will have them on Wednesday for you. All right. Find me my derivative.
Is that a 6 or a B?
It's a 6. All right, what's the derivative of 5x to the third? 15x squared. What's the derivative of e to the x? What's the derivative of ln of x? Derivative of 6. Okay. Awesome. How do I go from here to here? How do I underderivative it? Okay. Okay, so I would have to go, this would have to be 15 divided by 3, right? And that would be the x to the third. Okay. E to the x still e to the x. 1 over x would become ln of x, which, yes, is one you would have to know. But how do I get that?
I don't think there's a way to, looking at the derivative, find.
There's not.
Okay.
So, yes. So we put what's known as a C. Because, as you said, there, if you take the derivative of it, it's all going to come out to be 0, right? So you don't know what that one happens to be. But we still need to have something there because that there could be something that existed there that I don't know. So when we're going backwards, we typically put a plus C. What you just did was the integral, by the way. So there's 2 different names for it. The typical name is integral. You'll also see in the book it's called the antiderivative. So the antiderivative is basically undoing the derivative. So whenever we go one direction, we have to be able to undo that or go backwards. All right. So this is known as the anti. Or integral. The symbol for it, which you will see, looks just like this. That's the symbol for integral. And sometimes we'll have a number there and there. That's a definite integral. Sometimes we won't. But that's the symbol you're going to see for integration. But in essence, all it's doing is undoing what my derivative is. Okay? So some of them, as we saw here, like the e to the x, you just have to know that it's still going to be e to the x. Or like the 1 over x, we have to know that that one is ln of x. So when you're looking at integration, this is basically the beginning of Calc 2. This is where you're going to start. Calc 2 is all about integration. All right. You do use derivatives in some of the integration rules, but you're basically doing nothing but integration. Integration is difficult in a lot of places because there are a lot of those ones that you just kind of have to know. they're not as easy to derive and just come up with like we were doing with the derivatives. We have some very specific rules for derivatives, and we can come up with pretty much everything from it. But like, if you see 1 over x, you just kind of have to know it's ln of x. Or like, then there's some other ones that we're going to look at as well. And as we did with derivatives get rid of information because we lose those constants at the end. And if we do it again, we would lose more information. So when you're going backwards, we have to somehow get that information back. If we have some points on it that I can use to find it, we can do that. If not, that's where that plus c comes into play. All right. Actually, before we do that, I want to do one more thing first. Basically. There's a lot of things that integration helps us find, which we're going to talk about next class. So, all right. So let's look at, what was it, 5x squared? 5x to the third. Let's look at this 5x to the third. So 5x to the third went to 15x squared. Because the derivative rule states what? It's x to the n is n x to the n minus 1, right? That's the derivative. So that's derivative. So the integral to get back, if we had x to the n here, and we want to go backwards, to go from 2 to 3, we would add 1 to it, right? So we have x to the n plus 1. Now, if I wanted to get back from 15 to 5, I had to divide it by that 3, correct? So it's divided by n plus 1. Okay, so that right there, that's my power rule for integration. That's the one that's going to be used most often. Right. So if I had, if my derivative was 10x squared, so what's the integral of 10x squared? Ten over 3 x to the third. This is just the product. This is just the power rule. What about integral 5? It's 5x. Think about this. If that would be the same thing as saying 5x to the 0, right? Because that anything to 0 power is 1. So you'd add 1 to it and divide by 1. So that becomes just 5x. What about 1 over x squared? What's another way that I can write 1 over x squared? That's the same thing as saying x to the negative second, right? Yes? Okay. So what's the derivative, or what's the integral of that? Or the antiderivative? So same concept, right? Negative. So I'm bringing 1, so it's x to the negative 1 divided by negative 1, technically. which I can then rewrite as negative 1 over x. Right? What do you mean?
The 1 over x squared, that's not a negative.
You're right. Doesn't have to be negative x.
If you put the minus 1 on top.
Oh, this at the end?
Yeah.
The negative could be in either top or bottom. As long as it's not in both. Because two negatives, if negative divided by negative is a positive, right? So as long as you don't have it in both, you can put it anywhere. You could have left the negative sign down the bottom, made it a negative x. Traditionally, you'd either write it on top or you'd write it in front. You don't typically write it on the bottom. But it's not wrong. So I didn't bring the negative 1 up front. I just moved the negative sign up to the top because I don't like them in the bottom. Okay. All right. So we've just done all this. What's the integral of 1 over x? Yes. But I just did a whole bunch of stuff with the power rule, right? What would that become? Using the power rule, what would that become? So this is the same thing as saying x to the negative 1, right? Okay. So derivative of that would, or the integral of that would be what? X to the 0 divided by 0, which does not work. Right. So that's one of those ones where inevitably you're going to do that. Okay? Because every other one works except for 1 over x. Okay? So that's 1 over x. This one ends up being, obviously, that's not right. And what it ends up equaling is ln of x. So, and we did it the same way when we were looking at in terms of, we did the derivative of ln of x, we went through and did the process of it, and I showed you how we ended up getting 1 over x. But inevitably, you're going to do this. Everybody does it at some point because it just makes sense. The key is most people will end up doing this and saying, oh, this equals x to the 0, which is 1. They'll forget to divide by the 0. And that's the piece that if you do, you're going to go, wait, something's wrong here. Okay? If it came back to be 1, that wouldn't make much sense, right? Because the derivative of 1 is gone, not x, not 1 over x. So it wouldn't make sense there either, but that's one of those ones that logically you're going to think it makes sense, but you can't divide by 0, so you're going to catch that mistake there. All right, so 1 over x does not equal 1 or x over 0. It equals ln of x.
So does this mean you can do the reverse of what L'Hopital rule?
I don't know, actually. I'll get back to you on that one. No, it's not. But you typically wouldn't, because the goal of the L'Hopital's rule is to actually simplify the problem. And typically integration makes it more complicated because you're adding more, you're going backwards in the process. But conceptually, I would think you could, but I don't think I've ever done it. So I honestly don't know if it would work. I'd have to try it. So because there are some situations where going backwards might actually be better, but like sometimes going more complicated, you can eliminate more information sometimes. But yeah, I actually don't know the answer to that question off the top of my head. I will look though for you, because that's an interesting little like thought process. All right. So This is a table of typical antiderivatives. All right, these are the ones that we typically will see. So if it's a constant, it's literally just the constant. It's the constant times whatever your x is. You can do same concept we were doing with addition. We can still do the addition of the pieces like you saw in that very first problem. We had multiple things. You just did the derivative of each piece. We could do the antiderivative of each piece. This one right here, that's that power rule that I was just talking about. The only one that doesn't work is when x is negative, when n is -1. That's that 1 over x. That one doesn't work. It is ln of x. E to the x is e to the x, as you actually remembered. B to the x is b to the x over ln of b. So going back, we would divide by the ln of b. So if you remember that it was the sines and cosines, remember it was sine of x. The derivative of sine of x was cosine of x. And then it was negative sine of x. And it was negative cosine of x. And then it repeated. That's derivatives. The antiderivative is going the other direction. So the derivative of cosine of x is sine of x. The derivative of sine of x is negative cosine of x because it goes backwards. Derivative of secant or antiderivative of secant squared x is tangent x. And then these are some of the other ones we had looked at beforehand. Because we went from the derivative of tangent of x is secant squared. The derivative of secant x is that. So remember, we were going basically from this direction. Now we're looking at, okay, if we've got this, we would go backwards for it. And as, yes. It's the hyperbolic cosine and the hyperbolic sine. I don't think I've mentioned those to you yet. It's the nice thing about these is they basically just reverse each other for sine and cosine. You'll sometimes see them, not very often. And that's why we typically don't cover them very much. But they're there, so they could pop up. Hold on. Let me see if I can show you a picture of it. So it's not going to make much sense, but basically it's not. That's the hyperbolic sine. It looks like a third degree function. It's not a typical trig function. So that's why I said it's not something that comes up often. This book likes to throw it on there. I put it in my book just because it's one of those more complex topics. But we don't use them very often.
Is that what she asked?
Yeah. It's a hyperbolic trig function. All right. So the integral of g prime of x is because the integral and the prime cancels each other out. So whenever it's asking you for what functions of g or what functions of h would equal that, you're looking for the antiderivative or the integral of it. So we're looking for the integral of what's over there. So the nice thing is I can split these things up. Also, one of the big things you're going to want to do, and I will tell you the hardest part, and I've said it even for Calc 1, but the absolute hardest part for Calc 2 is algebra. Because integration is a very annoying thing to do in certain situations. Undoing anything in any respect typically is harder than doing it. So integration is that respect. So when we're looking at integration, a lot of times we want to try to simplify the problem down as much as possible or rearrange situations so that I can use easier ways to do it. This problem, the 4 sine x, pretty simple to deal with. This over here, not so simple to deal with. Okay? It looks like it's kind of like just the power rule that we were doing because it's got a bunch of x's, but I've got a quotient in there. I've got divide in there. And as of now, I haven't told you any way to do integration with division or antiderivatives with division. So the way that it's written right now, I can't do it. Can I rewrite that though? Yeah. I can rewrite this 2x to the 5th over x minus the square root of x over x. What's 2x to the 5th over x equal? That's 2x to the 4th. Square root of x over x? Yeah, remember, that's the same thing as saying x to the 1/2, right? So this is 1 over. Actually, I'm going to rewrite this as a negative. So it's x to the negative 1/2. So it's 1/2 minus 1. 1 over the square root of x is absolutely correct. It is the exact same thing. However, the first thing you're going to do to that is then change it to the 1 over x to the negative 1/2. So I just figured I'd do it in one step. Because now I can use the power rules that we've done on it. All right. In this section, you typically will see them write this with the capital letter to go backwards. So g of x. What's the derivative of 4 sine x? Or sorry, I keep saying because that's what this is. What is the antiderivative of 4 sine x? Almost. Negative 4 cosine x. Because we're going backwards, so it's the negative 1. So it's negative 4 cosine x. Yes, the constant does not change. Same thing when we were looking at it in terms of taking the derivative. The constant didn't change. So if I was doing the derivative of that, it would have been positive 4 cosine x. All right, what's the derivative of 2x to the 4th? Two divided by 5. So one of the things that you have to be careful on is you want in derivatives, you brought the thing down and then you subtracted the 1. When you're doing the antiderivative of the integral, you're adding the 1 and then you're bringing it down. So it is x to the 5th and then 2/5. Because you're dividing that 2 by the 5. So you add it first and then deal with the number. All right. What about the x to the negative 1/2?
1.5.
Almost. Yes. Yes. 1/2 power. So it's going to be x to the 1/2 power, because that's adding 1, right? Divided by 1/2. Yes. And when you're dealing with some of the rules in integration, when you have to do them both in the same problem, it can get really confusing on the direction you're going. And it is the number one mistake that people make when they're doing these with the power rule is you go the wrong direction. Yeah, I'm going to do that in a second because I'm going to clean this up a little bit. Yeah. This I don't have to rewrite. This is fine. And this I'm going to write as 2 square root of x plus c. And the plus c comes in because, again, I don't know if there was a constant there originally, so I need to keep that in mind.
You just put plus C or plus minus C?
Nope, just put plus c. Because c can be anything. So if c was negative, it'd be plus or negative, which is fine.
Yeah.
So you don't have to necessarily worry about that piece.
Is there a way to find C?
Yep, that's the next problem we're going to do. One step ahead. All right, so we're gonna, because I don't think you couldn't have written it down that way. Remember, -1 just means it's down the bottom. So what's the derivative, or sorry, I'm going to literally say it constantly. What's the antiderivative of e to the x? E to the x. Okay. The 20 is a constant, right? So I'm literally just going to put the 20 out front. So that now is 1 over 1 plus x squared. What is the antiderivative of 1 over 1 plus x squared? That was one of those ones on that table. So go back to the table. That's that one right there. It's the arctangent. So tan -1 of x plus c.
How did they figure out that was Andy? Play probably because Andy that.
Yes.
But I think it was well.
So that's why, actually, I'll show you because it's weird. I think I can share this. Hold on a second. I got to switch something over here so I can share my screen instead of. So here's your actual book, which I don't think any of you have actually really looked at. Does it not have it? Hold on. Does it not actually have it at the end? Oh, that's weird. This book doesn't actually have it.
That's why we haven't.
All right. Hold on. I will find it. As I know what I want to show you. All right. So here, this is a list of derivative rules. One page. Okay. That's the list of derivative rules. So he's got some derivatives up here. So he's got all, here's the list of derivative rules. It's one page, right? Here's a list of integral rules. And that's not even all of them. Okay. Most books have at the end of the page, at the end of the book, about 187 different integral rules. Not every one of them you'd have to know. Like, there's a lot of them you could figure out. But that's where, like I said, going backwards is a lot more complicated than going forward.
Set of papers from the book.
That actually was from Paul's notes online.
Oh, okay.
Every other textbook that I've had, I guess, before this one, actually has them at the end of the book, and I don't know why this one doesn't. They're normally like in one of the appendixes, they have all the actual integral rules, and they didn't for this one. And like I said, I don't know why. Yeah. Yeah. I can do that. I'll find the more complete one though. I'll post that one. Huh? Yeah. No, he's gonna put it under his pillow. Yeah. All right. We're not done with this problem. They gave me more information. So the only way, if we were to look at this one, so actually graph this one. So when we're looking at the derivative, it loses information, as we said. So plus x. All right, so this is this function. All right. However, C can be anything. So it can shift up and down for any of those values. So this problem gave me and said that when f of 0, so that's the x, the answer is -2. So I would shift this one so that at 0, I have -2. So in this case, my C is -3. So remember how I said you don't have to do the plus or minus because C will tell you what it is? In this case, my C is -2. So now let's go back to this, figure out how to do that. Because, oh, -3. Yes, -3. How we got that. We have this information. We're going to plug it in. So I know f of 0. So I have e to the 0 plus 20 times the arctangent of 0 plus c equals -2. So what's e to the 0? What's the arctangent of 0? Yes, because the angle that would give you 0 is 0. So I have 1 plus c equals -2. So c would be -3. So when I write my final statement, my final equation, I don't have to put minus plus c there. I put -3. And that would be the answer for the problem. So the only way for us to find that is they need to give me other information about my problem to be able to figure that piece out.
So they have to tell you what it's related.
They have to give you something. They don't necessarily have to tell you the 0. They can tell you any value. But they have to tell you a value where the graph goes through. Otherwise, we don't know which one it is. It would be any of them. All right. Your turn.
This is the last unit, right?
No, we're going into chapter 5. I don't do 4.9, and I don't test you on 4.9 because 4.9 is basically leads you into chapter 5, and I never found the point of being like adding integration to the test on the derivatives. So this in chapter 5 is all the beginning of the integration. So this leads right into that one. So in my book, this was the first section of the integration unit, not the end of the derivative unit. All right, what do they give me? They give you the second derivative, and they want the original function. So you're going to have to go backwards twice. For the first one or the second one?
For the original one.
Oh, the original function? Then no. We'll see the second one.
Next.
Do it one step at a time.
Yeah. The second one's -4. First one, no. Okay, so it's X4.
they have two constants at the end?
No. You have to do it one step at a time. So when you take the first derivative or get the first derivative, which you find C, you have C.
That's where I messed up.
When you find the next one, that C now becomes CX. We don't know what it is yet. We have information to find it. We don't know what it is yet.
I just didn't know what CX.
Yes. Sometimes they will give you the information as they will give you the first derivative point, so you can find the C originally there, and then do your next then the next antiderivative. In this case, they didn't. They gave you 2 points for the original problem, so you have to go all the way to the original problem first. So now we have f of 0 is 4 and f of 1 is 1. So if I plug in 0 to everything cancels out except for D. So D is 4. So now I have now if I plug 1 in for everything, I get 1 equals 1 plus 1 minus 2 plus C plus 4. So 1 plus 1 minus 2 is 0, plus 4 is 4. So this becomes 1 equals C plus 4. So -3 equals C. So my final answer is -3x plus 4.
But if we get multiple constants, just mean that different things, we don't know if they're the same.
Yes. And there's so when we start playing, we won't do it here in this stuff. But when you get into Calc 2, you will have situations where you will have multiple constants. Sometimes you have to name them as different things. Sometimes you can just literally combine them together. Just have one C at the end. Like if you have C plus D and there's no X's or anything else on them, you can literally just write that as plus C because it doesn't make a difference. In this situation, because we were doing the derivative or the antiderivative again, that C now has an X on it. So you don't want to name the next one C because they would have to be two different numbers in this situation. So, and you can use some people use like C1, C sub 1, C sub 2, C sub 3. You can use basically any letter you want except for the letter that's the variable that's in the problem. So like I wouldn't use an X for this, but any other letters would work. C just happens to be the term they use for constant, and that's the one that's stuck. But all right. What was the one application? So when we're looking at, there was one big application that we did that the first derivative was something, the second derivative was something else. And they told me information about what the original thing was doing. Yeah. Yeah. So the position was my original function, right? The first derivative was my velocity. Second derivative was my acceleration. So if you think about when you're driving your car, Which one of those three things do you know? You know your velocity, you know your speed, right? It might be helpful to know where your position is. So that would be an antiderivative. If you knew your velocity and you're going backwards, we could figure out where our position is. Which, if your velocity wasn't changing and it was 60, okay, what would your position be? 60x, right? And x would be whatever the time, however long you've driven. Okay, so we can, and that would tell me exactly where I am at that point, like how many miles I've gone. All right, so in a car example, it's very simple and very straightforward. However, things can become more complicated when we're looking at other particles and other objects. So in this problem, it says a particle moves in a straight line, its acceleration given by 6t plus 4. It's given me its initial velocity and its initial displacement. They want the position function. They want to know where it is. So they gave me my acceleration. So your acceleration is typically your what? That's the second derivative. Okay. So to find my velocity, that would be my first derivative, right? I would have to take my antiderivative. So what is the antiderivative of 6t plus 4? Yeah. Plus 4t plus 6. So you were told that the initial velocity was -6. That means you plug in 0 for t. So in this situation, you're absolutely right. However, as we've seen in other problems, it doesn't always work out to be that exact number depending on what the function is. In this case, all my t's vanish. So yes, c is going to be -6 in this case. Because they gave me that information right there. Now, unlike the last problem where you had to do the two antiderivatives and then plug in your values for it, this one they gave you the value for your first derivative or your velocity in the situation. So we were able to plug it in and find c immediately and not have to find c at the end like we did in the last problem. All right, so we're at the velocity. We need to find our initial position, right? So we're going to now look for my first statement. So we have to do the antiderivative again. So what is the antiderivative of 3t squared plus 4t minus 6? Minus 6t plus, I'm going to use d just not to confuse the c above it. Yeah, this one, you plug in 0, everything's going to disappear. So in this one, I used 0, -6. And this one, I'm using 0, 9. Right here. So my initial point, or my position function, t to the third plus 2t squared minus 6t plus 9. And that's my initial displacement. or my position function. Does that make sense? All right. What were we given in this problem? That would be my yeah. What does it actually give you that? Oh, it doesn't. Okay, I got to give you a piece of information. All right, so they told me my initial velocity is 48 feet per second, and they also told me where we started, right? 430 feet above the ground. Okay. Does anybody know the gravitational constant?
9.8.
9.8 meters per second squared, right? Okay, but this is in feet. Anybody know it in feet?
Why would I know?
This is the horrible system that we live in the United States where we like feet. 32 feet. I wouldn't have known it either until I looked at it.
I know it's like roughly 30 or something.
Yeah, it's 32 feet per second squared. And since we're throwing it, the acceleration it's actually going to be negative because it's going to be dropping, right? So it's negative 32 feet per second squared. All right, so there's my acceleration. Find me my position function. You can ignore the units at the end, by the way. Give me a problem with the ball hitting the ground. All right, what do we got? What's my velocity? And plus C, but yes, when we plug in 48, it's going to be negative 32T plus 48. Because it says upward, positive. If it was downward, it'd be negative. All right. What's my position function then? Was it? Plus 48C. I'll use D for this one. And then we're starting off 432 feet above the ground, right? Plus 432. We're going to finish that problem in a second, but I want to show you something. There's your standard pre-calc problem when you were doing quadratics, trying to figure out where the ball was going to hit the ground or where things are. That's the equation they typically gave you. And it was always negative 16T squared plus something T plus some number. That's where it came from. Because this, that right there, that's a constant. That we know. That's the acceleration of gravity. So as long as there's no other force accelerating the object, like it's not a rock, this is just a ball. So there's no propulsion on it. So it's just the gravitational constant on it. And you can figure out from there, that's where that negative 16 always came from that was in your problem. I remember in high school, my students asked me, why is it negative 16? And obviously they don't know calculus, so I couldn't go back through and explain the whole concept behind that part. But it's like, that's where that came from. So, all right. When does it hit the ground?
That's just when y equals 0.
Yes. So where does it hit the ground? That's 32 divided by 60. How would I find this? Yes. So let's pull out the negative 16 because that's going to make my problem more annoying. So that's negative 3t or minus 27. Yes. And there's no numbers that multiply to 27 and add to negative 3, right? Not that I can think of off the top of my head. So you have to do what? Yep. So b squared minus 4ac. So we've got 9 minus 4 times 1 times negative 27, which is 108. Plus 9 is 117. So I've got negative 3 plus or minus the square root of 117 over 2. It's obviously not going to hit the ground at the negative version of this because that's going backwards. So then the correct answer would be t equals negative 3 plus the square root of 117 divided by 2. Oh, you're right. It is negative b. You're right. It is negative b in front. Thank you. Yeah, somewhere around there. Oh yeah, I'm not done yet. I got a little more than one more though. All right, let's do.
Just double check.
Yeah.
1.5, right? So 27 times.
So you'd have your vertex is negative b over 2a. So yes, 1.5. Yeah, 1.5 would be the time where it's at its peak. So it's not exactly from because you're throwing it up, so it's going to peak first, and then take a little longer to go down. So because remember, so it's like the plus or minus of this. So there's still another one on the other side. Yeah. Other, well, yeah. So, all right. Oh, I didn't because be stupid. I didn't realize that was one of the questions. It does say that. Yes, 1.5. I missed that part of the question.
That's just the first story.
Yeah, you could absolutely do the first derivative, take that to 0. I did it from this one, but yeah, you could definitely do that one. Because you have negative 48 divided by negative 32, which is 1.5. But I had the initial problem down here, so I just found the axis of symmetry, which is this negative b over 2a. So either way, it works out fine. Oh, we're not doing that problem. This one. There we go. All right. So we're going to find a derivative first. We'll start with one of those. We'll do this one. All right. Find me f of x, or f of theta. Then we'll do a
Taking next week, we're learning how to do the other foods.
of integration.
Yeah, we're just going how to do that.
No, that's calc 2. Uh-huh. Believe it or not, that stuff becomes really complicated. We're gonna do very simple situations. Next, on Wednesday's class, we're gonna actually learn what integrals actually help us with. One of the other pieces of it's not just to undo things; they actually do give us actual practical information. So we're gonna look at that information too.
To realize.
Yeah. What's the antiderivative of sine? Yeah. What's the antiderivative of cosine? Plus c. They give me this information. So at this point, 0 and 4. What's cosine of 0? Sine of 0? So C is 5. So now, what's the derivative of negative, or what's the derivative of negative cosine of theta? Negative sine of theta. Derivative of cos or sine theta? Plus 5 theta plus d. And they give me a point here as well. So 3 equals 0 minus 1 plus 0 plus d. So d equals 4. So there's my original function.
Negative sign.
So if you ignore the negative sign, what's the derivative of cosine? Or what's the antiderivative of cosine? It's just sine. You're going the other direction. So it's just sine. So the negative sign is just -1, which stays in front of it. So here. Hold on. Let's see if I can find one that's all on one page. I'm trying to find, hold on a second. I'm trying to find one that's quick, that's all on one page. All right. We're going to go, we'll do that one in a second. So while, here we go. Give you a little head start or a little, you would think that, so this is the original problem for this one was x squared e to the x. Okay, simple multiplication, right? Except we have to do something known as integration by parts to do it. So, and what we end up getting at the very end, so the original function for this one is x squared e to the x minus 2x e to the x plus 2 e to the x. Okay. So here. Oh, watch. What's the derivative of that? Find me the derivative. So if we look at this first, right? Before we do this, before you even find the derivative of this, right? What do you notice is in every problem? So let's pull that out. That's going to make my derivative a little easier, right? Because I have a multiplication, so I have to do the product rule. So e to the x goes to e to the x. X squared minus 2x plus 2 goes to what? Two x minus 2. All right. So f prime of x it's the derivative of the first, right? So that's e to the x times the second plus the derivative of the second times the first, correct? Yes? Okay. So I have e to the x squared minus 2x e to the x plus 2 e to the x plus 2x e to the x minus 2 e to the x. Because that cancels out with that, and that cancels out with that, and we're left with that. So to go from that to that takes some work because it's not implicitly obvious how you get there. Okay. And that's where a lot of the stuff in Calc 2 comes into play. That's actually chapter 7.
So we can get to that.
Not in this class. No. No. All right. Let's look at this problem. Last problem we're going to do. 15 milliinches. So where does the car stop?
Squared.
Yeah, 22 feet second squared. That's the,
Squared.
huh? Yeah, the acceleration is always squared.
Ask her a question.
Yes.
Is acceleration negative? Does decelerating?
Yes.
Interesting.
All right. So what are we starting with? Well, I know my velocity is 50 miles per hour when the brakes are fully applied. I know that. But velocity is going to change over time, right? Because of the brakes being applied. So I know my the brake deceleration. So my acceleration is negative 22. So my velocity would be what?
Negative 22t plus 50.
Negative 22t.
Those are two extensions. That's 50 miles.
Oh, you're right. Right. Darn it.
Which is our.
Good catch. Very good catch. All right. What was it? 73?
73.3.
Okay. So 73.3 feet per second. Good catch. I missed that one. All right. So we want our because my acceleration is not changing. It's a constant 22 feet per second. It's kind of like gravity. But that's actually, so when we're looking at cars, that's actually a very important thing to realize, like, is to figure out what is your braking deceleration rate. Like, that's a constant. So, and depending on how worn your brakes are, that can change. So, all right. So, what's my position? Negative 11 t squared, 73.3 t. And we're going to assume we're starting at 0. Right, from when we push the brake. So that's at 0. So my C is going to be 0 in this situation. All right, so we want to know when the car comes to a complete stop. So that's when my velocity is 0. I would have to close my velocity that to 0. So V of 0 is 0 equals negative 22t plus 73.3. So I've got 73.3 over 22 equals t, which is approximately what? 3.33? 3.33333. Yeah. All right. So now if we plug in that into my position, we will get how far we took to stop. Which is approximately 122 feet. So if you're going 50 miles an hour and slam on the brakes, it's going to take you 122 feet to stop. If you're going 60 miles an hour, because I just literally quickly did that, it would take you 132 feet to stop. So if you are right behind the car in front of you,
That's why it's like the second.
right. So if you think about it, we said it should take us about 3 seconds to stop, right? So, and it's 4 seconds actually, if it's 60. So when you're looking at it, like, you're going to assume the car in front of you is not going to a dead stop immediately. So they're going to be slowing down too. So you have that extra piece in there as well, but it's still, plus you have to add in your reaction time and everything else. That's why we look at those things. I used to do an example in my high school classes where we figured out how many feet per second it was for miles per hour, and which we just did there. 50 miles per hour is 73 feet. 60 miles an hour is 88 feet. Classroom's normally about 40 feet long. I said you're traveling 2 classrooms in a second. It brings in 60 miles an hour to a whole new perspective. When you think about you're traveling literally 2 lengths of this classroom in 1 second. And that's just 60. Go on the highway today, people are not doing 60. Right. But that's why, unfortunately, accidents happen, is because reaction doesn't work that fast.
Windshields, like in a car, you're isolated.
Yeah.
Outside, you have no perspective of how.
It's because the stuff is traveling around the same speed as you. So the perspective isn't there. Have a good day. I'll see you guys on Wednesday. If you look outside, look at your trees, you'll notice it. But even that, it's like it's further away, so the perspective wise, but since everybody's traveling around the same speed, it doesn't feel like you're going that fast. Yeah. This one?
Thanks, Professor.
Oh, the other direction. This one? This side?
Our meeting in the library.
Yeah, there you go. That's basically all of it was there.
have a,
I'm wondering if we should meet somewhere else because we're gonna be kind of loud. Like presenting. I know those rooms are closed off, but
Alright,
also you could try and crack on us like if we see them.
I mean, I don't, you know, we're not doing it.
Generally, there's no one by the tax surplus. Right, it's all like books and stuff.
Yeah. Not that sounds just one person.
We could do the.
No, I wasn't talking.
We could do the, sit down, so there's one of the window cups over on top of that.
No, it's fine.
You got 10 minutes. All right. Let's look at WebAssign. All right, chapter 4 homework, right? Okay. Remember what question it was?
There's a couple on there that I was having trouble with.
Okay. Just give me the number. I'll pull up an example of it.
So this one I was having trouble with.
5? Yeah, that's about 5. I'll pull one up on the screen, so if you want to start and start over there.
But just like one part of it.
All right, let's look at it. So this is 5. Right? Different numbers. The numbers might be different. The red numbers can
That being
change.
said, I actually just looking at that, I'm pretty sure I might have just had the wrong variable in there. So let me
That
check
could be
again.
true. That would totally screw you up.
My thing was 3x squared minus 16, and minus 14. Let me just check that.
Yeah, probably put the R and you should be fine.
Okay, yeah, so that one fix that problem.
Okay. And so sometimes it's just like, and that's why it's saying sometimes looking at the answers, it's like you're not using the answer to cheat. It's like you're using the answer. It's like, okay, that was the mistake. It's like it was a little simple thing. It's like you understood what you're doing.
Okay, my next one was 12.
All right, this one's a little longer.
And I have that one also part of the way done. I just got like stuck midway through and you have to like do each step.
All right, so we've got got the symmetry part and stuff, the domain.
Okay, so I have the domain, the X and Y intercept, I clicked no parent symmetry.
Yep.
And then I had the Y prime, Y,
Second prime.
yep. And then that was where I got stuck. I had the X equals does not exist, and then the Y equals I couldn't figure that out.
Okay.
Also, your thing might not be on the screen.
I didn't put it up there. All right, so that's what they got there. we'll just look at those. All right, so the next question was vertical and horizontal asymptotes. So horizontal is when the problem goes out to infinity, and you said does not exist, which is correct. Because I don't have, so your x is your vertical asymptotes. So I have no vertical asymptotes in this problem. I do have a horizontal asymptote in this problem. So the horizontal asymptote, we actually go back to the original problem, which was square root of x squared plus 2x. Which one did you have? X squared, what was your
Plus 5x.
plus 5x? Minus x. So we're looking at this as it goes to infinity. Which means we have to use the L'Hopital's rule. So this is the one we did where you have to do the conjugate pair
Mhm.
because we have to get it to the derivative, or we have to get it so we can do multiple on it. So we're multiplying the top and bottom by x squared plus 5x plus x. Same thing on the bottom. So my top, so the bottom is just the square root of x squared plus 5x plus x. And my top comes out to be x squared plus 5x minus x squared, which is just 5x. On the top.
And then plugging in infinity for that.
Well, if you plug in infinity,
Oh wait, then you just find the derivative.
because you'll end up getting infinity over infinity, which doesn't work. That's plus 1. All right, so
5 over. It's like infinity over infinity, right?
yeah,
So is it just 5 over 2 or no? Or wait, no, infinity over infinity, does that become 1 or no?
huh? This,
Then you plug in infinity, right?
yeah. So this ends up going to 1 because this goes to 0.
Which one goes to 0?
Why is the answer 1? Hold on. Hold on a second. Something's up in this one. Oh, wrong paper. Oh, we didn't actually have to do, that's why. We didn't have to do the antiderivative. I mean, we didn't have to do the L'Hopital's rule. We could have divided everything by x. Here. This is the one we did in class. I forgot that. If you divide everything by x here, you end up getting 2 on the top. So in the problem we just did, you'd end up getting 5 on the top and 5 on the bottom. So it should come out to be 1.
And the intervals for which it's increasing.
So this one, you're just looking at so increasing and decreasing, you're just looking at the first derivative. So we want to know when, so we have to find our critical numbers because that's going to give me the interval, the breakpoints. So we want to know when 2x plus 2x minus 1 equals 0. Huh? Yeah.
It's like the same.
Yeah. So we can bring the 1 over and then multiply by the bottom. So square both sides. So we get 4x squared plus 8x plus 4. Yeah. Equals 2x squared plus, no, not 2x squared. Four x squared plus 2x, which is 4x squared plus 8x. So actually we end up getting 4 equals 0, so there is no place where this is going to equal 0. So remember there's 2 possibilities for critical numbers. It's where it's going to equal 0 and it's where it doesn't exist.
So this doesn't exist.
This one doesn't exist when x is 0.
Would that be the same for decreasing as well then? So
You're welcome.
There's no critical numbers at all.
Well, increasing and decreasing. No, once you find there is critical number. There's 2 sets of critical numbers. It's where the derivative equals 0 and where it doesn't exist.
Oh, where it doesn't exist.
Right. In this case, it doesn't exist when x is 0. Because if x is 0, my bottom, the fraction is going to be 0. Okay. So my critical number is x equals 0. So now I can set up my thing to plug a point on either side and figure out if it's where it's increasing and where it's decreasing. So if we plug in 1 and -1, if I plug in 1 here, I get, again, all I care about is this is positive or negative. So I'm going to have 4 on the top and two times. So is it bigger than -1? Actually, you know what? Let's pick a bigger number. Sometimes picking a bigger number makes it easier. It's going to be the same. Because remember, all we care about if it's positive or negative, right? So in essence, I just need to know that it's going to be bigger than bigger than 1. Because if it's bigger than 1, it's going to be positive. True?
Yeah.
So if I plug in 5 here, I just need to make sure that it's going to be bigger than 1. So I would get,
Also, I just want to double check really quick. I had the problem, so I did the 2x squared plus, or no, 2x plus 5 squared.
oh, this part?
Yeah, and I had 4x squared plus 20x plus 25
Yes.
equals, still 4 on the other side.
Right. But it should be x squared plus 5x, which still should cancel out your 4x squared and your 20x.
Oh, yeah, because you have to square it. Yeah, yeah, you
Yeah.
square on that side as well.
Yeah, you still have to, yeah. So what do I got? 2 times the square root of 35? So that's less than 6, right? Square root of 36 is 6, right?
Yeah.
So this is going to be less than 12. So that means that's bigger than 1. So that's positive. You could also just plug it in a calculator. And that side's going to end up being negative. So it's increasing from 0 to infinity and decreasing from negative infinity to 0.
Then next was concave up and concave down.
So you're looking at where this is going to be positive and negative,
Which one?
the second derivative.
Okay.
So if we just look at this one, again, find my critical numbers. So since this one can never equal 0.
And my problem was negative 25 over 4 times x squared plus 5x
Okay.
to the 3 halves.
Okay. Same concept. Still can never equal 0. Because there's no variable in the top. So I know it's not going to be equal 0. So we're looking for where it doesn't exist. So we're looking for where the bottom equals 0. Because that's where it's not going to exist. So mine, I got 0 and negative 2.
And then mine was 0 and negative.
So you're going to do the same thing. We set up our breakdown and pick some numbers. So let's do -10, -1, and 5. And I'm using Desmos this time because I don't feel like trying to do this in my head. So if we plug in -10, I get negative.
Mhm.
If I plug in -1, I get undefined. So it doesn't exist there at all. And if I plug in 1, I get negative.
1 is negative and negative on this.
So that means it is concave down from negative infinity to -2 for mine, -5 for yours, and 0 to infinity. And it's never concave up because it's never positive.
then local minimum and maximum was the last one for this.
So how do you find the mins and maxes?
That's also with critical numbers. Is that critical numbers with your just original problem?
No, that's your first derivative is going to tell you where your mins and maxes are. But your mins and maxes are where the first derivative equals 0, right? Did my first derivative ever equal 0 in this problem? No. So there is no min and max. If you had a number, you can then use the first derivative to figure out where it's positive or negative, to determine where it goes into. Or you can use your second derivative to figure if it's concave up, it's going to be a minimum. If it's concave down, it'll be a maximum.
Okay, so that helped me on that problem. And oh wait, it said that it's for mine it says y does not equal 1 for the horizontal and vertical asymptotes.
Yeah. So your vertical asymptote is y equals 1. Or your horizontal asymptote is y equals 1.
And saying that it's not.
Hold on. I wonder if it's because of the 5. Oh, okay. So I wonder if it's just... Okay, hold on. Let's figure out why this one was 1. Because yours is x squared plus 5x. So you have 5 there. Oh, it's 5 over 2. And then your interval isn't from negative infinity to 0. It's negative infinity to negative 5. For your concave up and concave down.
Okay.
Got it now? Okay.
And on question 9, it was stuff with like cosine and sine. Also, if you have somewhere to go, like it's okay, we don't have to do.
I just have to go back to the high school group. That's all. So it's fine. Like, I'm helping you. That's the exact same session. So, either way. And there's nobody over there until after lunch anyway. So. All right. So this one. All right. Okay. So there's my equation. Which numbers did you have?
X cosine squared x minus 12 sine x.
Okay. All right.
Yes.
Okay. So your first part was asking which is it increasing and which is it decreasing, right? Okay. So finding out when the interval is increasing and decreasing, it means we have to find my first derivative. So what's the first derivative of this?
Let's see. That would be 6. Or no, 12. And then cosine goes to just sine. So 12 sine x,
No, cosine goes to negative sine.
negative 12 sine x minus
Almost.
12 cosine x.
Nope.
Plus
You missed
12
something in the
cosine.
beginning. You have to do chain rule because of the square. You brought it down. You forgot to multiply it by that piece. So so in essence, we get 12 cosine x times negative sine x. And then minus 12 cosine x. So 12 cosine x sine x minus 12 cosine x.
Can I take a negative 12 cosine x?
Yeah. All right, so we're looking at where they wanted where it's increasing and where it's decreasing. So we need to know where this equals 0. Is in essence what we need to do next. So equals 0. So cosine of x equals 0 when?
Is it pi out? Is it with unit circle?
Yeah.
I don't remember that trick to look at it.
Well, cosine starts at 1, right? And goes down. So it's going to go down. And the nice thing about sines and cosines is it's always zeros and ones on the actual axis lines.
Yeah.
So it's 0, pi over 2, pi, 3 pi over 2. So 0, so it starts off at 1. So 1, pi over 2 is at 0. So it's pi over 2.
Okay, and that's
And
what
then
I had in my original thing, but I got confused. On
Then it's negative 1 at pi. And then it's 0 at 3 pi over 2. Okay, so that's the cosine ones. Now, sine of x minus 1 equals 0. So we really want sine of x to be 1, right? Whereas sine of x 1. Sine starts off at 0, right?
pi over 2 and 3 pi.
Right. So I've got those two values there. All right. So those are the endpoints. And I know I'm starting off at 0. So I've got 0, pi over 2, 3 pi over 2, and 2 pi. So I need a number in between each one. So let's do pi over 4, can do pi, and 7 pi over 4. So we just need to know when those are. So let's plug in negative 12. We're still looking at my second or first derivative. Negative 12 squared. I really can't type today. All right. So pi over 4 is positive. Hold on. I typed this wrong. Oh, that would be why. I'm in degrees. I'm like, wait a second, something's wrong here. All right, so pi over 4 is positive. Pi is negative. Okay, that's better. And 7 pi over 4 is positive. All right, so we got that. Does that make sense?
Yes.
All right, so it's increasing.
Negative infinity to 0, or no, negative infinity pi over 2.
Yep.
And 3 pi over 2 to
Oh, not
2
to,
pi.
yeah. And it's not to
0
infinity and
to-
0, yeah. I forgot this was only from 0 to.
0
So-
pi over 2, and then I couldn't figure out the 3 pi over 2, so that's where I was getting stuck. Cause I had
Gotcha.
the pi over 2 in my problem, but not the 3 pi over 2.
Yeah, that would totally screw you up. And then it's decreasing from pi over 2 to 3 pi over 2.
And then local minimum and max. Local minimum would just be I mean, if we plug this problem in on the graphing calculator, wouldn't we be able to visually see?
Yeah. Why is that? Hold on a second. Decreasing. We have this backwards. Where do we mess up signs? Well, your local minimum is maximum you can figure out from where it's increasing and decreasing. But we have this backwards. It should be minus plus minus. The question is why? Where do we screw up a sign? That's 12 cosine x times negative sine x. That's fine. That's negative 12 cosine x. Oh, there's the mistake. That should be a plus 1. That's the mistake. It doesn't change our actual answers for the pi over 2 and 3 pi over 2. Because sine would only be negative at 3 pi over 2, which is still there. It does switch. It switches our increasing and decreasing them. And it was literally completely, it was exactly backwards.
Okay.
So swap those. Dumb signs. Okay. So we now can use this. So I know that pi over 2, it was decreasing going into it and increasing out of it. So that's going to be a minimum.
Mhm.
And 3 pi over 2, it's increasing in and decreasing out. So that's going to be a max
And then you plug them in
to the
you have
original problem.
negative 12 and 12 for those values. Which I typed that in. That's what it said.
Yeah. Yeah. You plug those back into the original problem.
Yeah.
All right. Now the inflection points we have to find are second derivative.
So negative 12 cosine x.
Plus one. Sine x plus one. Because we pulled out the negative sign. That's where it switched the sign. All right, so that's my first derivative. So
That becomes just 12 sine x in the front, right?
Yep. Well, no, you have to do your product rule.
Twelve sine squared x plus 12 sine x minus 12 squared. 12 cosine squared x, which is what I have.
Okay.
I can take out a 12.
Yeah. All right, so now we have to set this to 0 to find my inflection points. So if we change, right now I've got sines and cosines in this problem, which is going to make a mess to try to figure things out. So let's change the cosine to sine, because I have more of those. So we're going to change that cosine to 1 minus sine squared x. So that means I have negative 12 plus 12 sine squared x. So that means I have 24 sine squared x plus 12 sine x minus 12. Pull out the 12 so I don't have to worry about that. I have 2 sine x squared x plus sine x minus 1. Okay. So if I set, if we just make like, let's say m is sine x, I have 2m squared plus m minus 1. If we factor that, we get 2m minus 1. I just did, yeah, 2m minus 1. And then m plus 1. So I have 12, 2 sine x minus 1, and sine x plus 1. All right. So now we can set them all equal to 0. So 2 sine x minus 1 equals 0, and sine x minus or plus 1 equals 0. So sine x equals negative 1, and sine x equals 1/2. So this one we know, that's 3 pi over 2. Where does sine x equal 1/2?
Is it just pi?
No, pi sine is 0. So pi over 6, if we just look at the first quadrant, right? So it goes, if you think about the little trick, it's 0, 1, 2, 3, 4, right? On the top. So the square root of 1 is 1. So that's 1 over 2. That's 1/2. So it's pi over 6. Because then the square root of 2 over 2 is pi over 4. Square root of 3 over 2 is pi over 3. And then if we go to the other side, because it's got to come back down, it's going to be at 5 pi over 6 would be the other one. Because it's just before it hits 0 again. All right, what were we trying to figure out?
Inflection.
Okay. So if we plug in those values, it's pi over 3, pi over 2, not an inflection point. Oh, this 3 pi over 2 is a 0. This 3 pi over 2 is a maximum value. So it can't be an inflection point. So does that make sense? That one is a maximum.
Okay.
So it can't also be an inflection point. Make sense?
Yes.
All right.
So we have pi over 6 and 5 pi over 6.
Right. So those 2 points, we have to plug those back into the original problem to find the actual answer. And they want the exact answer, so you can't just plug in Desmos and get the. Actually, you can. The scientific calculator will give it to you, because it's a fraction. At least it should. What was the original problem? What was the original problem?
Mm. 6 cosine squared x minus 12 sin x.
Nope, it won't. So pi over 6. Oh, okay. It gives you a number easy enough to figure out. So if you plug in pi over 6, we get negative 1/5 or 1.5. So it's negative 3/2. And if we plug in 5 pi over 6, we also get
Oh.
negative 3/2. So those are
Oh, yeah,
your
that
two
would
final
kind of make
points.
sense. I think.
Yeah.
And
Alright.
it's the interval that it's concave up. You can kind of look at the graph for that, right?
Yeah, but so yeah, if you're looking at your graph of the second derivative, so if you graph the second derivative, sine x one. So if we look at this one, it's negative from 0 to pi over 6.
So
So it'd be concave down because this is the
0
second
to pi over
derivative.
6.
So 0 to pi over 6, it's negative. So actually, we'll shrink this down a little bit. 0 to 2 pi. There. All right. So from 0 to pi over 6, it's negative.
As well as over there on that other side.
Yeah. So from pi over 6 to 5 pi over 6, it's positive. So this will be concave up. And then from pi over 6 to actually till 2 pi, it's all negative. But it's not okay. So when you type this in, you have to exclude 3 pi over 2. So you have to write it like this. So it's concave up from pi over 6 to 5 pi over 6. That one's easy. It's concave down because it's 0 at 3 pi over 2. It's not concave up or concave down, so we have to exclude that value. So you can't just say from 5 pi over 6 to 2 pi.
This is really helpful that you're going through these because I don't think that I would have been able to.
Yeah, you'd have missed little pieces on them.
Yeah. And then like it's hard with Desmos, like you miss little pieces and it's like hard to know exactly where you went wrong or if you even just like typed in the wrong thing.
Yeah, like the R.
Or not Desmos, the
Yeah, WebAssign.
Yeah.
That's why, as much as I know, like the multiple step problems are annoying, I like them better because at least you know that it's not, okay, I've done all this stuff, I put my answer and it's wrong. Where did I screw up? At least this one, it's like, okay, here's a piece. Okay, I know I got this one right. I know I got this one right. I know I got this one right. Oh, this is where I made my mistake. Let's figure out where this is.
okay, so it's so I thought the inflection points were
It was pi over 6.
negative 1.5, right? or -3/2.
-3/2, yeah.
Which is what I have, but it's saying it's wrong.
That's weird.
5/6 and 5/6.
Hold on. Oh, wrong problem. This was what, 9, right?
Yeah.
5/6 and 5/6. We got those. They have -3/4, but that's a different problem. Those are my inflection points. We plug that back into the original problem. Process this. Yeah. Let me see. I wonder if you typed it wrong. Don't put the parentheses. They already had them.
Oh, okay.
I'm like, no, that's the answer.
Like those were like the tiny things.
Yeah, those are stupid little things. Exactly.
The actual answer of that.
Right.
It's just the- And then, number 15. I got through a couple steps of it, about half.
Okay. So you got the volume, step 1.
I got the equation for.
Okay.
I got step 1 completed.
Okay.
And then step 2, I got the equation for H, and then I got the volume minus 1200 B, and then the parentheses B to the third over 4.
Yep.
But I wasn't figuring, like, I'm not sure what that next thing is asking. The equation is valid when B is less than something times the cube root of 3. Or sorry, the square root of 3.
Okay. So we're looking at. So the base has to be greater than 0. So oh, okay. So in essence, we need to figure out where b to the third over 4, that piece is going to start being bigger than my original problem of the 40. What was your number in front of b?
1200.
1200. Okay. You have 1200. You have 1200 b minus b to the third over 4, right? Okay. So b has to be greater than 0. That kind of totally makes sense.
Yeah.
So, but if this is bigger than this, it won't work, right?
Yeah.
So we need to figure out where that's going to be true. So where is b to the third over 4 greater than 1200 b? We'll set it equal to, and then we'll go there. So we get b to the third equals 4800 b. So b squared equals 4800 squared.
So it's the square root of 4800.
Yeah, except there's a 3 in there because they gave you that part. So I think it's 1600.
Oh, because
So it's square root of 1600 times 3, which should be 40 square root of 3.
okay.
So they want the 40 because they already got the square root of 3. They already gave you the square root of 3. Because that's remember that real life restriction we were talking about before? It's like, you don't, like mathematically, it doesn't matter. I can put any number I want in there. But realistically, that doesn't make sense.
Yes.
So that's what they're looking at, that piece there.
And then this, I feel like I could probably figure out the,
Yeah, that's just looking for the maximum. So you do the first derivative of it, and
so
then
that one I think I can figure out the rest of. And then on 14, I was just having a problem like making that first equation.
okay. So we've got a.
Like
I know the
my
number will be off, but what's your how many
there's-
million square feet?
37.5.
Seriously, thinking 37.5.
Yeah.
Mine's 6. Like 37.5.
Yeah.
Okay. A lot of square feet. All right. It doesn't make much difference. Okay, so let's make our picture. So we've got a farmer wants to fence an area, rectangular feet, and then divide it in half. The fence parallel to one of the sides. So we've got rectangular field. And then we want to cut it in half. I guess it doesn't actually really matter which direction we decide to cut this. Okay, so this is y, that's x, and x. So my area of the field,
It's just x times y.
it would be just x times y. So the area is just x and y. So you got what, 37.5? I think they want these in millions. Yeah, so times 10 to the 6th equals xy. So if that's, divide that by x and you get y. So that's that. Okay.
Yes.
So now my perimeter is 3x plus 2y.
Yep.
So it's 3x plus 2 times 37.5 times 10 to the 6th over x. Or 3x plus 75. Yeah. So that's your function for perimeter.
Okay, so I was kind of close to that, but I missed. I didn't do the times 10 to the 6.
As long as you, yeah, they want times 10 to the 6th. If you did all the rest of the work, like if it was a regular problem in the real world, not in WebAssign,
Yeah.
if you didn't put times 10 to the 6th, but you knew that at the end, it wouldn't have mattered.
Yeah.
But they want the times 10 to the 6th. And then find the second derivative, or find the first derivative of that, and then set it equal to 0.
Does finding the first derivative of the one with the 75 times 10 to the 6, is that like harder than?
No, that's just a constant. That's like 3. You can ignore it really when you're doing the
Oh,
derivative.
'cause isn't it ln of? No, that's the thing.
That's the opposite direction.
That would just be 3 plus.
And then -1 over x squared. Because it's x to the negative first. which ends up being negative, which goes to -1 x to the -2nd. So we end up getting 3 minus 75 times 10 to the 6th over x squared. And then we set that equal to 0.
Find the critical numbers.
So we bring the 3 over. So we've got 75 times 10 to the 6th
Yes.
equals 3x squared divided by 3. Square root of that is 5,000. And then you plug that back into the original area problem. And you can figure out why. Or just plug 5,000 into the y problem. So 37.5 times 10 to the 6 divided by 5,000 will give you y. And just make sure to put it in the right spot, small or larger.
Okay. Should just get that scientific method real quick. About 30,000 equals y.
No.
Let me see it. Parentheses.
You divided it by 5,000?
Yeah. It's 1,500 plus.
Oh, first the original problem. So 37.5 times 10 to the 6 divided by 5,000. What did you do?
Oh, it's the first derivative, not our original. Oh, wait.
No, it's the original. It's the original y.
Okay, so it's 3x plus 75 times 10 to the 6 over x.
No, use the original y up here. Remember we had y equals?
Oh, yeah.
Plug it right into there.
$7,500.
Yes, that's right. Is that all of them?
Alright, so my original thing, f of x equals 3x minus 75 times 10 to the 6 over x.
3x plus 75 times 10 to the 6 over x. Yes.
Okay, so then I plug now I have y equals 7,500 equals 3x.
Wait,
Oh no, then I'm just doing area, right? For this last, no.
the last one, they just want the smaller value and the bigger value. So it's 5,000 and 7,500. You actually have to do no calculations for it.
Okay, it's just asking.
Yeah, it just asked what the dimensions were.
Okay, I think
That is a
asked me,
really long fence.
like, what are they even using that for? and that helps me out. So, thank you. Sorry that this took
Oh,
so
no, you're
long.
fine.
but That was very helpful.
You're fine. That's the point of this. That's why they're paying me all the big bucks.
Yes.
Oh, I'm leaving. You're fine.
For a second, I thought it was the wrong last one.
Nope, normally I'm not here by this point. I'm gonna have to edit the I totally forgot to stop recording. That's fine.
Thank you so much.
You're welcome. You too. I'll see you Wednesday.